Hello and welcome to our online Acids and Bases Chemistry course. We're here to guide you through the course and help you to think about how to teach acids and bases and to get the ideas across in the classroom. Just a couple of things before we get started. If you haven't already done so, please download and open the companion sheet before going any further. This sheet contains links to key resources and some questions we will be considering on the course. You can take as long as you want to work through this course. Use the content page to find the bits you're most interested in. And don't feel you need to work through the whole thing from start to finish. At various times throughout the course, we will ask you to hit the pause button to allow time to work through the activities. So let's get started.
When your students hear the term acids and bases, what do they think of? Is it the exaggerated image of acids eating away at substances, as often portrayed in the media? And sadly, we also hear about acid attacks from time to time on the news as well. In contrast, have they ever even heard of the word alkali? And for base, do they think of the bottom of an object, or even base in the mathematical sense? Do they think the difference between a strong and a weak acid is actually how fast it eats away the substance? According to education research, many Pre-16 students hold some or all of these views.
When starting to teach acids and bases, it is important to know as a teacher what your students already know. Think about the progression of ideas and be really clear with the use of language. A good starting point is to recognise that acids and bases are all around us and have been for centuries. For example, many acids are found in food and drink. There's also stomach acid, and acid can be found in bee stings. Examples of alkalis are common in household cleaning agents and also indigestion remedies. And there's other examples, bicarbonate of soda in baking and also wasp stings.
Many of the acids and alkalis that students come across are colourless liquids, so students will also need to recognise the need for some sort of test or indicator to work out which is which. pH indicator paper can also be used and colours compared with a pH chart. And also pH meters or probes are commonplace in many schools, which allow a digital reading of the pH value to be measured. Being aware of the common misconceptions helps anticipate the difficulties students may encounter in their learning. So, we are going to consider some statements designed to reveal common misconceptions in understanding acids and bases. Read each of the 6 statements here in turn. Decide whether the statement is true or false. Pause the video while you do this and restart it when you are ready. So now you've had a chance to write down true or false. Let's consider the answers and find out some of the difficulties and challenges students face, all of which will be picked up at some point in the course. This first statement is false because concentrated acids don't always have more H+ ions if, say, the concentrated acid is weak, and if the dilute acid is strong, then it may contain more hydrogen ions. Again, number 2, this second statement is false for similar reasoning to the last point. Now, these first 2 statements highlight the difficulties around understanding the differences between the terms strong and weak, concentrated and dilute, which often get confused. The third statement highlights issues around equilibria of water and its ions, raising the point that the ions are present in solutions. There are some ideas and tools for visualising this submicroscopic level that we will consider later on. The fourth statement is true. Sodium hydroxide does contain H+ ions, not so many, but they're still present. This statement reveals an understanding of the pH scale. pH always measures the hydrogen ion concentration and not the hydroxide ion concentration. The fifth statement is true. Here we meet the idea that an acid or alkali can be strong yet dilute at the same time. Students need to learn the basics and be able to identify acids and bases from their formulae too. In this case, that hydrochloric acid is a strong acid. Whenever terms such as dilute or concentrated and strong or weak are introduced, they must be explained clearly so that students understand that they have quite different meanings. Number 6. The words base and alkali are often used interchangeably instead of being used correctly. An alkali is a soluble base, therefore the final statement is false. We need to be really explicit about the use of language here in order for students to understand the difference. We will be picking up on all these difficulties just discussed at different points during the course.
Let's summarise the key difficulties students have with acids and bases. There is confusion between the terms strong and weak, and concentrated and dilute. Students often think acids burn and eat away materials. What are bases and how it reacts? What the key pH scale measures is also a problem. Identifying acids and bases from their formulae. Neutralisation is often viewed as removing the properties of an acid. If you're interested in finding out more about students' ideas and perceptions about acids and bases, we suggest you read Chapter 8 of Beyond Appearances, Student Misconceptions about Basic Chemical Ideas, where you'll find a summary of the key difficulties and challenges faced by students and suggested activities to challenge these fixed ideas. You'll find a link to this document on the companion sheet. So what's the best way to introduce the topic of acids and bases to your students? The thread of ideas is common to all the courses in the series and shows how the ideas conceptually build upon each other during secondary education. When and how do you introduce the topics to your students? What difficulties do they encounter? Now take a moment to reflect upon your current teaching order. There is a link on the companion sheet to a Word copy of the thread of ideas which you may find useful. Please pause the video and take a look. How does your teaching route compare to the thread of ideas? Great! Now that you've done that, let us now consider the pH scale. Here we see a typical image seen in many textbooks, showing the relationship between pH and the colour of universal indicator paper. Take care when introducing this to your students, as it can store up issues for the future, such as students thinking that neutral is green, rather than having a pH of 7. Or hydrochloric acid has a pH of 1, but if it's diluted, the pH of course can be higher. It's also worth remembering that the scale in theory can be any number, including negative numbers, such as -1, or it can include decimal points, such as 6.9. The pH is only limited by solubility and the maximum concentration of the substance in water. These ideas are beyond the scope of Pre-16 chemistry, but it's useful to be aware of them, as students can often ask testing questions about exactly how far the scale can go. If you're interested in finding out more about how the pH scale came about and the maths behind it, there is a section on this in our online Teaching Math Skills course. You'll find a link on the companion sheet. You may also find this activity helpful, as it puts meaning behind the numbers in standard form by linking to the magnitude of familiar objects. Many students find standard form very challenging. Maybe discuss this with your own maths department. Find out when they introduce it. Also allow time for plenty of practice. In school, the pH scale is often introduced by allowing students to test some laboratory acids, alkalis or household chemicals for themselves. They can do this by using universal indicator paper or solution, or a pH probe. Alternatively, another activity is to use this PhET simulation. Here the students choose from a number of substances, put it into the beaker and then add in the pH probe, where they can see the pH. By adding water and diluting the solution, you can see how the pH changes. If you have access to a lab, a good activity to introduce the general idea of dilution to alter pH is to simply ask students to keep adding distilled water to a starting acid or alkali and recording the pH. It is important to realise that you can only dilute from either direction to a maximum of pH 7. Later students will learn about the tenfold difference in concentration between a single unit of pH of a strong acid or a strong alkali. Follow the link on the companion sheet to access the simulation and short how to use video guide. You'll find that there are two different versions of the simulation. The one here provides a pH of the foods at the start, whereas the one on the PhET website does not. You'll find both links on the companion sheet. In a moment, pause the video to reflect on how you could use these simulations with your students. For example, you could use it when there is no access to a lab or to support retrieval practice. Pause the video now.
Students making and testing their own pH indicator, for example from red cabbage or other plant material, is a simple and satisfying activity. Various red, pink or blue flowers or berries give distinct colour changes for acid, neutral or alkali. This activity can be done either at school or at home. Click on the link found on the companion sheet to watch the Royal Society of Chemistry's YouTube video of chemistry in your cupboard called Red Cabbage Rainbows for full video instructions on how to make red cabbage indicator solution and paper. You will also find an explanation of the background chemistry and a pH colour chart. Pause the video while you do this. If you don't have access to red cabbage, don't worry. Depending on the time of year, you could try out some flowers. This is another activity which could form the basis of a practical for home learning. Spices such as turmeric also make good indicators. As you can see, yellow for acidity and neutral, and bright red for alkaline conditions. Neutralization circles is a quick and simple introduction to indicator colour changes. Ask your students to observe and then explain all the colour changes they see from the point at which they add a drop of universal indicator to the filter paper, which has already got a drop of acid and a drop of alkali on it. And the paper can be dried and stuck into students' books as a record of the colours. Full instructions can be downloaded from the education website. You will find the link on the companion sheet. Combining the challenge of making a natural indicator with neutralization circles makes a suitable project for students to work on, using the materials available either at school or at home. At home, filter paper can be replaced with kitchen paper towel or coffee filter paper. Vinegar or lemon juice and sodium bicarbonate solution, a bit of baking soda dissolved in water, can be used for the acid and alkali. When red cabbage indicator is added to the paper, this is the result. As the paper dries, the colour becomes more distinctive. This type of activity also helps to develop your students' practical and problem-solving skills, and it also makes a good piece of project work.
Rainbow Fizz is another great demonstration that always goes down well with the students. Declan Fleming has it down to a fine art. In this demonstration, a solution of sodium carbonate is added to a tall container, such as a burette or measuring cylinder, containing dilute hydrochloric acid and a little universal indicator. As the two react, the rainbow and fizz makes a wonderful display with many points to discuss with your students. Follow the link on the companion sheet to watch this demonstration in Fizz Revisited. The complete video is 7 minutes long, with the first section being suitable for younger students. The middle part, from 2.4 minutes, is more suited to post-16 chemistry, so you may wish to skip this part and jump to the final section, which shows some more fantastic colour changes. The video page also comes with instructions on how to do the demonstration.
Confusing language. Is it a base or an alkali? These words are often used interchangeably, when in fact they have clear definitions and students need to learn which substances are bases and which are alkalis. Bases are often defined as substances that can neutralize acids and vice versa. Alkalis are soluble bases. This should be made very clear to students, as often they hear a mix of the two terms, alkali or base, as if they are interchangeable. This can be summed up by a Venn diagram, and yes, there are some substances that can react as both an acid and a base. For example, aluminium hydroxide. These substances are known as amphoteric. While we're extending into post-16 ideas with this, your most able students will sometimes ask challenging questions, so it's good to be aware.
We can use the periodic table alongside some practical activities to help students learn and recall the differences between bases and alkalis. Metal oxides are basic. You could also encourage your students to download the periodic table app, which is freely available for both types of mobile phones. Metals in Group 1 react with water to produce alkalis, such as sodium hydroxide. Reinforce this idea by demonstrating the reaction of alkali metals in water. If you add a few drops of universal indicator into the water trough at the start, you will be able to observe the colour change from green to bluey purple as the metal hydroxide is formed. A link to the experimental details can be found on the companion sheet. Don't forget to do a risk assessment and practice it in advance of the lesson if you haven't done it before. The oxides of metals in Group 2 are sparingly soluble in water. They are able to react with acids in a neutralisation reaction.
It is possible to show your students the pH when non-metal oxides are dissolved in water. Burning sulphur in oxygen, adding water in universal indicator solution shows a clear colour change from green to red. A really easy way to show the pH of another non-metal oxide is to blow carbon dioxide into a solution of universal indicator and observe the changes in colour and therefore the change in pH. The green indicator solution, pH 7, changes to yellowish orange with carbon dioxide, showing that it is acidic.
These ideas lead us into discussions about acid rain and ocean acidification. Here we can see the effects of acid rain on a forest and a stone wall. Secondary age students are required to be aware of key global issues such as anthropogenic causes of climate change and other environmental issues. So it's a great opportunity to put learning into a real context and help students to understand some of the global issues the world is faced with.
In the Royal Society of Chemistry's Assessment for Learning website, you'll find many useful resources including this one. What are the effects of acid rain? It is a great way for students to learn about acid rain through hands-on experience of planning and carrying out an investigation, followed up with a short fieldwork task to identify and record evidence of the effects of acid rain in their local environment. These tasks provide a focus for students' thinking, discussion and action that will develop investigation and group work skills, so is ideal for project work. Or if curriculum time is limited, would make a good STEM project, as it will take a number of weeks to complete all the tasks.
Scientists around the world are concerned that ocean acidification will double by the end of the century, having a devastating effect on many different types of ocean species. Another important global issue. So why not use some of the fantastic ocean acidification resources from Encounter Ed, including their PowerPoints, videos, student sheets, or ideas for practical work. Pause the video and take a look through the resources for both acid rain and ocean acidification. Consider how you will make use of them with your students. Full details are found on the companion sheet. So, what are the issues with neutralisation? Many young people think that neutralisation means an acid is breaking down. This idea may come from everyday experiences. They have little or no understanding that particles are reacting at the submicroscopic level. A good way to introduce this and get round it is to introduce the idea of neutralisation through a reaction between acid and a base, and then use Johnson's triangle to work out what has happened. Alex Johnson suggested that chemistry knowledge is understood at three fundamental levels, or representations: the macroscopic, the symbolic, and the submicroscopic. The macroscopic is found at the top of the triangle. This is what we see or observe. The symbolic level is at the bottom right. This is what we use to represent what we have observed, through, for example, word or symbol equations, mathematical formulae, graphs or diagrams. The submicroscopic level is at the bottom left, and this is what is happening at the atomic level. We need to use models to describe this. Pause the video and have a go at completing Johnson's triangle whilst watching the microscale neutralization in a drop clip. You'll be able to download a triangle template from the companion sheet along with the link to the video. To find out more about how to use Johnson's triangle with your students, have a look at the 7 Simple Rules article. Develop deeper understanding with models. The link is also on the companion sheet.
Examples of neutralization reactions are often used in the context of teaching about exothermic and endothermic reactions. Students can feel that the test tube or beaker is very warm when an acid reacts with an alkali and recognise this as one of the familiar signs of a chemical reaction. Now, this can be used to help your students understand what is going on during neutralization reactions, as this heat energy given out is the net result of bonds breaking and new bonds forming. You can do this by measuring the changes in temperature as well as pH after every addition of acid, as it is added to an alkali, and then plot out the graph. Plotting the values shows the maximum temperature occurs at the neutralization point. While the procedure lists a burette for doing the stepwise additions of acid, a smaller dropping pipette or transfer pipette, for example 1 cubic centimetre, can also give effective results as shown here. Using a pH sensor and data logger produces some good results. You'll find links to the practical activities on the companion sheet.
How many times do we hear or see the phrases acid plus base makes salt plus water, or acid plus metal produces salt plus hydrogen? It's written in textbooks, revision guides and on web pages. Perhaps you're thinking, what's wrong with that? Well, it leads to the very common misconception that all salt is sodium chloride, the stuff you see in seawater and have on your chips, when in fact there are oh so many different types of salts. Here you see salt pans in Gozo, Malta, where salt harvesting is only done during the summer period. To avoid students making this mistake, it is better to say acid plus base produces a salt plus water, or acid plus metal produces a salt plus hydrogen. Then provide them with lots of practice for naming salts and writing equations. This is also good for retrieval practice.
Making a soluble salt from an acid and base is a core experiment in many chemistry curricula, but it is also true to say that if students follow the traditional method of making copper sulfate, then it is one of the class practicals that records the highest rates of accidents or incidents in the classroom. There are, however, other ways of preparing stunning crystals of copper sulfate which are very straightforward and take a very short time. Pause the video and watch the alternative methods. Reflect upon the pros and cons of using the alternative methods. You will find links to these on the companion sheet. Pause the video now.
Titration is a technique used by analytical chemists to determine the concentration of an unknown solution by reacting it with a solution of accurately known concentration. It can also be a tricky topic to teach. If you'd like to find out more about titrations and how to teach them, then have a go at working through the titrations topic on the online quantitative chemistry course. Here you will see how you can break down this technique into a sequence of much more manageable chunks. Also have a look at our titration screen experiment, which is great for students to work through. You'll find the links on the companion sheet. Pause the video while you have a look through them.
Confusing language. The classic confusion regarding acids and bases is to mix up the terms strong and weak with concentrated and dilute. They have entirely different meanings in this context. Strong or weak refers to the degree of dissociation, while concentration is a measure of the amount of solute in a solvent. Perhaps our own everyday language can share the blame for interchanging these words. How often have you heard someone ask for a weak cup of tea or a strong cup of coffee when they really mean more or less concentrated? So it's important to be clear in the early stages about not using the word strong or stronger because they mean something different in this context of acids and alkalis, and there are simple alternatives. Instead, we can use phrases like is more acidic or more alkaline and put the emphasis more onto literacy. It can be worth going over with your students at an early stage, pre-16, that they know exactly how to use the related words that are subtly different, that an acid is the noun, acidic the adjective, describing a solution. And alkali is the noun or thing, and alkaline is the adjective describing the solution.
Practical activities show the differences in conductivity, pH and reactivity also help students to understand the differences between strong and weak, dilute and concentrated. A really helpful way to show the difference between strong and weak acids is to carry out a series of reactions and observe the differences. For example, a fixed amount of sodium hydrogen carbonate to a fixed volume of 1 molar hydrochloric acid and then the same volume of 1 molar ethanoic acid. Further experimental details can be found on the companion sheet. An effective way to show the difference between concentrated and dilute is to carry out sequential 1 to 10 dilutions. Starting with a solution of 1 molar hydrochloric acid, we observe a pH of 1. If we dilute by a factor of 10 to 0.1 molar, we observe a new pH of 2. Such an experiment provides some evidence to support the statement found in many pre-16 specifications. As the pH decreases by 1 unit, the hydrogen ion concentration of a solution increases by a factor of 10. This leads nicely into a modelling activity.
Making physical models can be a really good way to get the ideas across to your students and often leads to some useful discussions. For example, we can use building blocks to model acid strength. The red and white blocks represent acid molecules, so when they're dissociated you get single red and single white bricks. The blue bricks represent some water molecules in the background. Now, your task is to decide which building block picture represents which, strong, weak, concentrated or dilute, in all combinations. Pause the video while you decide what each model is showing. Then when you're ready, you can restart the video to reveal the answers. Great, you've had a go at that. Now let's have a go at the answers. A is a strong acid which is concentrated. All the red and white paired bricks are split apart. It's fully dissociated, so it's strong. B, well, that's a weak acid that is concentrated. So most of the red and white bricks are paired and not split apart. Only a few are split apart, so it's not fully dissociated, so it is weak. C is a strong acid that is dilute. It's dilute because there are only a few red and white bricks in total compared to the others. D is a weak acid that is dilute, for similar reasoning. You could use this type of activity to check the understanding of your students, especially if you ask them to give a reason for each answer. It is based upon Keith Tabor's acid strength diagnostic probe. You will find a link to this on the companion sheet.
These ideas can be reinforced and taken further using the advanced pH simulation, and you can start to explore the logarithmic scale. You'll find a link on the companion sheet. Pause the video whilst you have a go. Reflect on how you could use this simulation with your students. Do you think there is anything in this simulation that could either help or hinder their understanding at this stage? Pause the video and consider this.
Now that you have completed this course, spend a few minutes considering what you will do as a result of your new learning. The images you see on the screen now provide a quick summary of some of the different things we have covered on the course, and you will find the intended learning outcomes on the companion sheet. You may find it helpful to jot down a couple of things that you would like to do straight away. Towards the end of the companion sheet, you will also find an action planning template, which you may find useful to complete as it provides a space for more medium and long-term planning. If you are interested in further personal development, please visit our PD page to find out what else is on offer.
For further classroom resources, please visit the following link or scan the QR code. Thank you for participating in this course. We hope you enjoyed it and got a lot out of it. Thank you and goodbye.
Inspiring your teaching and learning.